Alright, so in this video, I'm going to take you over acid-base equilibrium. Okay, I've got a number of questions that I want us to answer together. Okay, so you can have just a quick um, look at them. Okay, so I'm going to answer all these questions up to question 10. I've done a few of other tutorial sheets before this one, but for this one, we're just going to answer these very questions that I've shown to you. Okay, let's get started. Every acid can lose a proton to become a base, and every base can accept a proton to become an acid. Species related in this way are called conjugate base pair. Okay, so basically, if you look at the in our context here given to us, we've got a definition just from there. Okay, so we can define an acid um, to be what? To be. So you've seen that an acid can lose a proton, okay, to become a base. So an acid is a proton donor. That's according to Bronsted-Lowry. And then, of course, a base on the other hand is can be defined in that same context as something that is able to accept what? A proton. Okay. Now, as we talk about a proton under acid-base equilibrium, think of it as the hydrogen ion, right? That's what is representing a proton. Now, let's get back to the questions before we get very far. So if you're new to this topic and want to learn it in full, in detail, from scratch, from all the definitions, and just deeply, you can just use the link in the description below. I've explained the topic from scratch. Okay. What is an acid according to Arrhenius and state its limitation? Okay. So unlike the definition given in the context above, an acid according to the Arrhenius guy, he defined an acid to just be any substance, particularly that increases. Okay, so the substance that increases the the hydrogen ion concentration. Okay, the hydrogen ion concentration. So of course I've shown you what an hydrogen ion is, right? The same proton. So any substance that's able to increase the hydrogen ion concentration when dissolved in water, okay, when dissolved in water, is called an Arrhenius acid. That's how Arrhenius defined an acid. Okay, so I've just written that for your sake. Okay, so that is according to him. Of course, on the other hand, you would define a base to be any substance that increases the hydroxide ion concentration when dissolved in water. Now, this definition has got a limitation. Okay, so the limitation is as simple as its limitation. It's limited to the aqueous solutions. Okay, so the Arrhenius theory is limited to the aqueous solutions and does not explain the acid-base reactions in non-aqueous solvents. Okay, for example, it cannot account for the behavior of ammonia, which is not in aqueous, okay, which does not actually produce the hydroxide ion directly when dissolved in water. Okay, so I think its limitation is it's limited to aqueous solutions and does not explain the acid-base reactions in non-aqueous solvents. Okay, B. Identify the acid-base conjugate pair in the following species. So just to bring you back to the context given, we are told every acid can lose a proton to become a base and every base can accept a proton to become an acid. Okay, so an example is this guy. That's an acid. Okay, so this acid has got an ability when dissolved in water to lose a proton. So if it loses a proton, this is what happens. So the hydrogen there will disappear. It has been lost. Okay, so the charge becomes negative and then the proton will be added right there. Okay, So I've written for you a dissociation reaction for this weak acid. Okay, this guy that has lost, we are calling him an acid. Okay, because he has donated a proton. Then this guy that has lost, or what the acid becomes after losing it, we can call it the conjugate um, base. Okay, the reason why we're calling it a conjugate base is on the other side we've already done equilibrium for the chemical introduction to equilibrium. We understood the importance of this, right? Implying that there is also a possibility of a backward reaction. So in the backward reaction, the conjugate base can gain that proton to give us back what? The acid. Its ability to gain qualifies it to be what? A base. It's a proton acceptor on the other side. Okay. So all the same, if you'd have a base on the left, a base would gain. Then on the other side, I can give an example of this guy. This guy would definitely gain a proton to become this, right? So on this side, this is called a base because it's able to gain. But then on the other side as well, this has got an ability of losing. So it can be called a conjugate acid. So let's now try to identify if this is true for all the given pairs there. So let's identify the conjugate pair. So let's identify the acid-base conjugate pair in the following species. So I think I've already done that for you for the first one. So this guy is an acid, then its conjugate base is that one right there. So we've identified that pair, and then if you try, okay, this is too basic for us to be answering this. So I would allow you to just pause the video and try to match them up. So when you look at this guy, we can clearly see that it's a base. Then that guy becomes what? A conjugate acid, because we can see the gain in proton, right? Then this guy, okay, it has lost, so it's an acid, and then that's its conjugate base. Equally, this guy has gained to become that, so this is a base, that's its conjugate acid. Okay, so we've identified the pairs. Very simple, straightforward. Now I love the next question, because the next question is asking us which of the following is or are not an acid-base conjugate pair. So just check the difference in terms is, has it gained, has it lost a proton. So looking at the first one, hydrogen sulfide, okay, are these pairs? Can we try to observe a gain or a loss in a proton between them? So there's a difference. This is 1, that is 2, so implying that this one, or that one rather, lost a proton, so this can qualify to be an acid, and then this one is the conjugate base, right? And that's why we have got a negative charge here, so that's fine. This is a pair, that's a conjugate, that's an acid base conjugate pair. Now let's look at the next one. We've got an hydronium ion and hydroxide. Can we see a difference? Which one has gained, which one has lost? Now this one has got 3, there we've got only a single proton in the hydroxide ion. So clearly we can't identify the acid, we can't identify the base just right here. This is not a pair, because there's a difference of 2 hydrogens, which is not possible. That's why we actually know that these are actually opposites. They all come from water, so only water can act as both a base and an acid. So if you compare this to this guy, you'll notice that water becomes what? Water in that case becomes a base. Okay, how does it become a base? Okay, I don't have to confuse you. In short, the hydronium ion that you're seeing there, this guy, the hydronium ion, is just the same as a proton. So a proton can react with water, Okay, so water in that case will act as a base. How? Because it's going to gain, so that it becomes that's very hydronium ion we are seeing. Okay, and then water can again react with hydroxide. In case of hydroxide, water now reacts as an acid. How? It basically gets to do it. As an acid, it's able to donate, right? So when it does donate, what do you expect? So water will become an hydroxide, um, and then the hydronium ion guy, what does it form? Because remember from the previous one where we had the hydrogen ion with water, what did we see? We saw the production of what? An hydronium ion, right? In that case, we saw water acting as what? It actually gained, so it was acting as a base. Now in this case, it will act as an acid. Okay, so there will be production of water and the hydroxide ion right there. So that is not a pair. I don't know why I wanted to go into the theories. How about that guy? We've got sodium fluoride and a fluoride ion. Can we see a gain or a loss of a proton there? Okay, don't just look at the sign, it will deceive you. So sodium is a spectator ion in this case. That's why its absence has caused a negative charge, not a proton. Sorry. Okay, so we can identify this to be an acid-base conjugate pair by just the loss of sodium. So it's not a pair. Okay, so that's it to question 1. Question 2. Here we are now asked to determine the pH. Every time that we think of pH calculation, the first thing that comes to my mind, I've used few formulas. pH in itself, whenever you see a P, think of negative log always when you're under this topic. Now negative log of whatever is attached, so in this case negative log of the proton, okay, or the hydronium ion if you wish. Then if I see POH, you'd expect that this is going to be negative log of what? Again, the OH itself. The addition of the two pH and POH is equivalent to 14. That's also a very cardinal formula that you need to know. Okay, I think these are okay for now. These are enough to help us. They are sufficient to help us answer the questions. Okay, so for the very first one, a blood sample with concentration of hydroxide ion of a blood sample with a concentration of hydroxide ion of, so hydroxide ion concentration has been given for the first one to be 1.20 times 10 to the power negative 14. Why am I thinking of negative 14? Negative 7. So what's easy for us to find here is POH, because we've been given the hydroxide ion concentration. So POH, I said, is a negative log of what? The hydroxide ion concentration, which has been given to be 1.20 times 10 to the power negative 7. Grab your calculator and punch that. Negative log of the hydroxide ion concentration of 1.20 times 10 to the power negative 7, I'm getting 6.92. This is a POH. The question is asking for a pH. I gave you a formula which said the addition of pH and POH is equal to what? 14. So in this case, if you make pH the subject of a formula, you end up subtracting 14 minus the POH, which is 6.92. What is the answer there? 7.08. Good. Pause the video and try out B. B is basically the same, because we're also given, now that one is actually even more easier. So pause the video and try it out. So we're given the POH to be 4.3. That's the POH. So POH is given to be 4.3. How do we find the pH? So I gave you the relationship between pH and POH. I hope you haven't forgotten. They are equal to 14. So if you've got one, you can easily find the other pH. It becomes 14 minus 4.3. 9.7. 9.7. Okay, these questions are just too simple for us C, we have 100 milliliters of 0.01 molar concentration of hydrochloric acid with 500 milliliters of water. Okay, what do we do there? Okay, so let's just straight away determine the number of moles in our HCl there. So hydrochloric acid, the number of moles of HCl is equal to concentration 0.01 mole per liter applied by the 100 milliliters, which is as good as 0.1 liters if we divide that by 1,000. Okay, so the initial number of moles of hydrochloric acid becomes 0.001 moles. These are the number of moles of the hydrochloric acid present. Okay, now what has happened there? We've diluted it. Okay, so the volume, the new volume, the total volume becomes what? The already existing 100 milliliters plus 500 milliliters, which is 600 milliliters, which can be divided by 1,000 to give us in liters, to be 0.6 liters. Okay, so we have 0.6 liters. So we have our new volume, we have the number of moles that were present in the initial concentration. So we can now find the new concentration because of the change in the volume. So therefore our concentration becomes the number of moles 0.01 divided by 0.6 liters. So that was mole per liter. What do we get? So if you want, you can use the dilution thing, which I believe should work properly as well. So concentration therefore becomes, after dividing that, we have 0.00167 molar concentration. That's our concentration of the acid. Now we do believe acid dissociates completely. So if we were to write down the breakdown of HCl, this is, I'll use a full arrow indicating full dissociation because it's a strong acid. So we have a proton and the chloride ion completely in the solution without the presence of HCl when dissolved in water. And so the concentration of the HCl, or the hydrochloric acid, is equivalent to the concentration of the hydronium ion that is formed after complete dissociation. So therefore we can easily find our pH with confidence based it on the negative log of hydrogen ion concentration of 0.00167 molar concentration after dilution. Okay, now what's the pH? 2.78 is my answer. Okay, good. Now finally we've got G. Do you have a confidence? Pause the video. Have the confidence to attempt this one. Try it out. Doesn't hurt to try out. So it's 0.40 molar concentration of ammonia solution with Kb. So we've talked about the constants K from equilibrium, chemical equilibrium. So you understand what the K stands for. You can use the ice table to come up with it. Now we are told ammonia solution. We believe we know what ammonia solution is, right? Ammonia is a base, right? So we are told 0.40 molar concentration of ammonia solution with the Kb of that. Now the question is, can we find the pH or the pOH? So the pH and the pOH are dependent on the hydrogen ion concentration and hydroxide ion concentration respectively. So if we can find any of the two, we can easily find pH or pOH. So this is the concentration of a base. It's not a concentration of hydroxide ion. Know that. So what do we do? So unlike the previous one where we just had to consider complete dissociation, where we said the concentration of hydrochloric acid is equivalent to the concentration of the hydrogen ion concentration. For the weak ones, That's where the equilibrium aspect of this topic comes in, because then you have to consider the ice table. For people who know what happens, you can even write the formula right away, but I have to demonstrate for beginners or starters. Okay, so ammonia is a base. Now, after dissolving in water, should I write the full equation? I don't have to, because water is a liquid, it doesn't appear in the K expression. Okay, let me just show you the full equation. So that is in aqueous solution. Let's assume that's aqueous, and then we have water, which is liquid, um, and then this is a weak acid, so it's not completely dissociated. It's actually a base, a weak base, um, and then we expect that it will gain a proton, so that it becomes NH4, positively charged. Um, what else is happening here? So water becomes hydroxide ion, which is our interest, right? Okay, so when it comes to the ice table, we know the initial concentration of this guy is 0.40, so that is what you call the ice, right? And then you notice that the liquids don't appear in the K expressions, and then initially when we started we didn't have any of the two, we only add ammonia. So the change, this is going to be minus x, because it's a reactant. Taught you that from equilibrium. And then these will be additions of x because they are being gained, or they increase as the reaction progresses. So you end up with just plus x and plus x. So you would understand that your K expression, which of course in this case is Kb, is going to be dependent on the products, which of course are just x's. So it becomes x squared automatically. That's what you should know just now, so that you don't have to always write the ice table, especially when you don't have sufficient time. And then you understand that on the left, the equilibrium concentration there is 0.40 minus x. Now we don't waste time to subtract or add the x to a constant because of a small value of our Kb. So that part is just cancelled away. Okay, so automatically what remains is Kb is equal to x squared over 0.40 from the ice table using the equilibrium concentrations. Now Kb, if you make x squared the subject, you have Kb multiplied by 0.40, right? Okay, so to find the value of x, it becomes the Kb now multiplied by 0.40, right? Square root of that. Now, if you go back to what I had written for the ice table, you saw that the x was representing everything that was on what? On the right. We had NH4, and then we also had the hydroxide ion concentration. They are all represented by x at equilibrium. So the x value will represent both the hydronium ion concentration and the hydroxide ion concentration, which is our interest. So, in short, when you see this question, a weak base, a weak acid, and then they've given you either value of Kb or Ka, okay, without any other initial concentrations other than the base of the acid, the formula just becomes x is equal to the square root of the K over Kb multiplied by the concentration of the base of the acid, 0.40. This will give you, for this case, since it's a base, it's a hydroxide ion concentration. So the hydroxide ion concentration will be found as Kb. Our Kb value is what? 1.85 multiplied by 10 to the power negative 5 multiplied by 0.40. This gives us 8.6 times 10 to the power negative 3 molar concentration. This is the concentration, the hydroxide ion concentration, because we are dealing with a base right there. Okay, we've got our base. What can the hydroxide concentration help us find? The pOH. So pOH, I said, is a negative log of what? The hydroxide ion concentration, which in this case is 8.6 times 10 to the power negative 3. Punch that on your calculator. I'm getting 2.07. So what is the pH? The question is asking us for the pH. How do you find the pH? 14 minus 2.07. 11.93. I hope you're learning. Question 3, which I believe this you don't even have to waste time here, just go on and answer it. Okay, pause the video and try out A. Calculate the hydronium ion concentration. I've already emphasized and tried to explain that hydronium ion is the same as the hydrogen ion concentration. Don't even be confused. So the pH can be written either the negative log of this or the negative log of that. So calculate the hydronium ion concentration with the pH of that. So write the formula for the pH. Negative log of the hydronium ion concentration. Okay, so let's attempt to make the hydronium ion concentration the subject of the formula. So divide both sides by the negative, you end up with negative pH is equal to log of the hydronium ion concentration, right? So, and then you know log, this is base 10 of course, so from your logs you would understand 10 can become the base on the other side, so it becomes the negative pH, and then is equal to the hydronium ion concentration. So in other terms, I'm just trying to show you my math skills. So if you try to make the hydronium ion concentration like I've done the subject of the formula, it just becomes 10 to the power negative pH, right? So therefore 10 negative 2.0 as our pH there. Okay, so 10 to the power negative 2.0 to the power 2, which I believe you understand. You're a mathematician. That's the same as 1 over 10 to the power 2, right? Which you can now say 1 times 10 to the power negative 2 molar concentration. You can use a calculator if you want to. The same question comes back. Pause the video and do the one for the pOH. So pOH is equal to negative log of the hydroxide ion concentration, and then you make hydroxide ion concentration the subject of the formula. It just becomes 10 to the power negative pOH, which is 12. So that's 1 times 10 to the power negative 12, right? We're just adding a 1 in front. Okay, of course this is concentration, very important. Question 4. Now we're dealing with the weak acid ionization. The pH of 0.0600 molar concentration of the weak monoprotic acid HA is 3.44. Okay, so if you want to understand what a monoprotic acid is, a diprotic acid, a triprotic acid is, I've answered another worksheet which involves questions about that, and like I said earlier, you can use the link in the description below to learn any other chemistry topic, including this one, from the basics to other tutorial sheets in the past and the past papers, to just help you prepare for exams the smart way. Doesn't matter where you are and where you're learning from. We've covered everything that can help you sufficiently. Okay, so let's answer this question together. The weak acid ionization. So the pH of the weak acid is given to be 3.44. Now what is the percentage of the acid that is ionized in this solution? So I have emphasized even just in this brief video so far that the weak acids and the weak bases ionizes partially. That's what distinguishes them from the strong acids and bases. So implying that it's not 100%. Okay? Unlike a strong acid reaction, I told you of HCl, I'll repeat so that you get it. So what the idea here is, if we are to form a salt, maybe sodium comes to react with a chloride, there it becomes sodium chloride, right? The concentration of the acid is going to be the concentration of the salt, because the acid is a strong acid. It has ionized completely. It doesn't exist anymore in the solution. Even that's the implication of that arrow. But then for the weak ones, they don't. So part of it ionizes, part of it remains. So you can now determine the percentage of how much are ionized of this weak acid we have. Okay. So the weak acid we have is HA. If we were to write its equation, it's dissociating into the hydrogen ions and the other part A representing the conjugate base. Okay. So if we can find the concentration of that, we can express it in terms of a percentage in respect to what we had started with for the whole acid, right? Okay. So what are we told? We are told the pH of a 0.006 weak acid is 3.44. Okay. So clearly you can see that the concentration has been given. Okay. The concentration of the acid is 0.06 molar concentration. Okay. Then the pH has been given. Now one thing that you know is that the pH guy is dependent on the negative log of what? The hydrogen ion concentration. So if a pH has been given, the pH can help us determine what? The concentration of that hydrogen ion, so that we can find it there and express it as a percentage of the acid's initial concentration. I'll repeat. The pH has been given. The pH is dependent on this guy, so we can find the concentration by using the pH. And if we find it, we express it as a percentage of the acid's initial concentration. So in the previous question, the third question, I showed you how to find that. If you make this guy the subject of the formula, you end up with what? 10 to the power negative pH. So 10 to the power negative 3.44. That is our hydrogen ion concentration. 10 to the power negative 3.44. If you want, you can punch that on the calculator so that it gives it to you in a way that is easy for you to understand, but it doesn't matter really. So the hydrogen ion concentration divided by the acid's concentration initially times 100 gives us the percentage ionization. Okay, so the hydrogen ion we've said is 10 to the power negative 3.44, which if you punch on the calculator it will give you something like 3.63 times 10 to the power negative 4. Okay, divided by the acid's initial concentration, which was 0.006, right? Yeah, that's giving me 0.605% ionization. Then the other question says now determine the Ka of the acid. Determine the Ka of the acid. So this is a case now where I can go on and write the ice table if you want. But I think I already gave you a short formula of going about it. But anyway, this is the ice table. Okay. Now, this guy, we're just from determining its what? We're just from determining its value, right? Remember we said at the start, all these are zeros, right? Because you only started with a weak acid. Of course, there's an x there, plus x, plus x. Now the value of x has already been found using the pH, okay, which we found to be 10 to the power negative 3.44. That was the concentration of the hydrogen ion, which of course in terms of standard notation, scientific notation, becomes 3.63 times 10 to the power negative 4. So that is the value of x, 3.63 times 10 to the power negative 4. Okay, that is the value of x, because x is equal to the equilibrium concentration of the hydrogen ion. So we'll duplicate it to all the other parts. Okay, where there's x, then there you can subtract 0.006 minus that same value. Okay, okay, so we've got the equilibrium concentrations now. From your knowledge of chemical equilibrium, this shouldn't be hard for you. So your K is going to be the equilibrium concentrations, which of course is this and that for products, which will be 3.63 times 10 to the power negative 4. There are 2, so it will be squared over the the reactant 0.06 minus 3.63 times 10 to the power negative 4 as well. Don't mind, I don't have enough space on top. I hope you've gotten what I've done there. So therefore your K value is dependent on that very basic calculation. Okay, so after all the computations, I'm getting 2.20 times 10 to the power negative 6. I hope we're getting somewhere under this topic. I hope we are. We're now on question 5. Question 5 is a very simple question. 0.25 molar concentration of propanoic acid with a K value of that is 1.34 times 10 to the power negative 5. B 0.10 molar concentration of aniline with a Kb value of 4.3 times 10 to the power negative 10. 0.05 molar concentration of sodium benzoate with a Ka value of 6.3. So please, if you're tired, feel very free to pause the video and continue afterwards. Okay, so only C seems a little bit unique from what we've answered so far, in that this is a salt, but then we've been given the value of its acid there. Okay, but we'll still break it down. Let's start with A. A can be answered just like the way I answered the previous question. Here we are told 0.25 molar concentration of propanoic acid. If you can remember your organic chemistry, you can even write the equation. That should be something like C3H5COOH. Okay, so propanoic acid, which we believe an acid of course would dissociate. It's not necessary to write this formula. I'm just writing to show you that I understand what I'm doing here. It becomes a negative, so that's the conjugate base. Now we are told to calculate the pH. We're given the concentration of the acid to be 0.25. Okay, so my tip to you is, if you don't know the formula of the acid, just use HA for it. Okay, HA, and then you say something like this. Okay, you know that from Brosted Lowry, you know that the acid will lose the proton, right? And then its conjugate base will remain. Okay, that's the same with what I've written there, although I haven't just shown that there's a proton. Yeah. So what do we do here? We know the acid's concentration. We want to find the pH. So we understand that the pH is dependent on the what? On the proton guy, the hydrogen ion concentration. That's where it's dependent. That's its dependence. So the other way, the only way that we can find, if we are to show the ice table, we understand that until we find the value of x, right? So you understand this is minus x, that's 0, 0 initial concentrations, plus x, these will just be x's, and then 0.25 minus x. So you know the K value is products over what? Over the reactant. So x times x, that would be x squared, over the reactant we have 0.25 minus x, so always just cancel that out, because it doesn't actually make a difference with a very small value of the K constant. Okay, so it's not necessary for you to write the ice table. I won't show it for the next step. So for the Ka value, that's 1.34 times 10 to the power negative 5, and then we can multiply it with a 0.25 on the bottom so that we can find the value of x squared. So you can square both sides, square root, square root. What you find is the value of what? Of x, which is of course both the conjugate base and the hydrogen ion concentration which was existing, right? So therefore your concentration there becomes 5.79 times 10 to the power negative 3. This is the hydrogen ion concentration. Okay. So you know that if you get at this point, the pH value is not an issue, right? So the pH value is just the negative log of that very concentration that we found there, which will be 5.79 times 10 to the power negative 3. Okay. You'll be able to get the value of the pH. So what I'm getting is something like 2.24. Now for the next one, it's a base. I want you to pause the video and just try it out without using the ice table, without going as far as using the ice table. I want to see if you're able to picture what would you expect. Okay. So you know what a base is, right? A base gains a proton. So you can write something like A, and then A has decided to gain a proton. What happens to it after it gains a proton? It becomes HA, right? So you can even put a negative if you want. So it becomes HA. This is a conjugate acid. This is a base. It has gained a proton. So we'll call this to be an aniline. Aniline, I don't know how you pronounce that. 0.10 molar concentration. Okay. And then we don't know where we're going there. But one thing that might be of your interest there is you can even remove this guy so that you can actually indicate that there's production of an hydroxide ion concentration. From Arrhenius's definition, a base should increase the hydroxide ion concentration. That's the better way of writing the formula. Right? Yeah. So therefore, initially when you started this reaction, you never had those guys existing. So you even know where I'm going, that the Kb value should be able to come out something like x squared again over the 0.10 molar concentration minus x. We'll cancel out the x, and then the formula goes back to the same way, the similar manner that our hydroxide ion concentration, since this is a base, is going to be the square root of the Kb value multiplied by 0.10. The Kb value is 4.3 times 10 to the power negative 10 multiplied by the 0.10. Okay. So ideally, that's if you try to substitute the value 4.3 times 10 to the power negative 10, I'm getting 6.56 times 10 to the power negative 6. Okay. After multiplying and determining the square root, then this is the hydroxide ion concentration. It can help us to find what? The pOH. Now I said whenever you see a P, it's a negative logo. So negative logo, whatever is attached, 6.56 times 10 to the power negative 6. And our pOH becomes 5.18. If you find the pOH, it's easy for you to find the pH, right? Subtract 14 minus 5.18, the pH becomes 8.82. Okay. Now let's look at the interesting one, unique in that they've given us a salt right there. Okay, so 0.05 molar concentration of a sodium benzoate with a K value of 6.3 times 10 to the power negative 5. Okay, so right away I would want you to understand that the product of Ka and Kb is equal to the ion product constant. Okay. Alright, so I hope you are enjoying this video. If you wish to access the solutions to all the remaining questions, including this very question, question 5, sign up on our site using the link in the description below. You're going to learn the topic acid-base equilibrium from scratch, understanding all the definitions of the acids, bases, looking at the several questions on the acid-base equilibrium, understanding the theories that you need to, looking at the past paper questions on the topic, and actually understand all the references I was making to the other topics like chemical equilibrium, chemical kinetics, stoichiometry, and all the other chemistry topics. In fact, all the other courses are equally available with all the story sheets, topics, and past papers to help you build confidence as you approach your assessments and the exams that await you. Okay, so if you've enjoyed the video, please feel free to share the link with your friends, and of course, yeah, register on the site for premium access and just more to help you learn more. Thank you very much for watching and have a lovely day.